This is Physics 2. And we're in Chapter 18. If I could spell chapter. 18, doing problems. The first problem we're going to do is number 8. So 8 wants to know the RMS speed of molecules in a gas. So we got speed, velocity, RMS of some gas at 20 degrees centigrade is to be increased by 20%. So this is going to be going, well, we're going to go up 2%, 2.0%. To what temperature must the gas be raised? All right, so thank you very much for giving me such a big eraser. And I'm going to increase it by 2%. Okay, well, we ask ourselves, RMS final is going to be RMS plus 2% more.
What?
So the RMS final is going to be 1.02 of the velocity RMS. Okay, well, now that we know that, we knew that before, but now that we know that, we got to go find some equation to use. So I'm looking at equation 18-5 on page, whatever page that's in, 18-5. All right, and I see that on page 479, and I see that the velocity RMS of some molecule is going to be the square root of 3 kT over m. All right, and so that's interesting. And so now we want to find the new speed. So what's the new speed? K is the Boltzmann constant. T is in Kelvin, and m is probably the mass, I would imagine. Let me look at that real quick. Page 479. No, mass is in kilograms. Okay, so mass is in kilograms, so that's fine. Well, anyway, in any event, voltage final is going to be 1.02 of the voltage RMS. So 1.02 is going to equal the square root of 3 kT final divided by m divided by the square root of 3 kT initial divided by m. And the k's go away, the 3 goes away, the m goes away. This is going to be the square root of T final divided by my initial temperature, which is 293 K. Because I'm at 20 degrees. Did I say I'm at 20 degrees? Yes, I'm at 20, way up there. I'm at 20 degrees, so I go 20 plus 273 to get myself to 293 K. All right, so now I square both sides of my equation, and I get temperature final 1.02 squared times 293. and I end up with 305 Kelvin. And then I say, well, you know, my original temperature was in Celsius. I should probably put my final temperature in Celsius. So I'm going to subtract 273 from that, and I'm going to have 31.8 degrees when I keep all the numbers in my calculator. And then I ask myself, do I have 3 significant digits? This is number 8. Yeah, well, I guess I have 3 significant digits, so I'd keep 3 significant digits in my final answer. Okay, so that's problem number 8. I'm now going to look at problem number 18. Problem number 18 says, estimate how many, well, that estimate, that means that whatever I answer is has to be right? Estimate how many air molecules rebound from a wall in a typical room per second. Assume an ideal gas of N molecules contained in a cubic room with sides L. So now this is going to be a drawing thing. Can I draw something? A cubic room. Okay, so there's L. There's L. There's L. Okay, so I've got a cubic room of L at a temperature T. Okay, well, I'm glad to know that. T. And a pressure P. Okay, so there's my, show that the frequency of with which the gas molecules strike the wall is some number. Okay, so that's good. So I know the answer. All I have to do is figure out how I'm going to calculate that answer for frequency. All right, so we ask ourselves, what is the time for the round trip? And we find the time for the round trip is the change in distance divided by the average velocity in the x direction. All right, so we'll do with that. And that's going to be 2L divided by the average velocity in x direction. And so that means I'm going to go that way, this way, and I'm going to strike both times. So that's the time that it's going to be. All right, well, because we're in this chapter, we're obviously going to have to use PV is equal to nRT. That's an N in case anybody's wondering. And it's a capital N. Number of molecules, nRT. And so we can rewrite that and say that N is equal to PV over KT. But we know the volume is L squared, so that PL squared, make it cubed, PL cubed over KT. So now that's something I know. I know the temperature. I know everything. Isn't that good? Yeah, that's pretty good. So my frequency of hitting the wall, what's that going to be? That's going to be the number of molecules I have divided by the time it takes to do a round trip. All right, so that's going to be N. Change average volume in the x direction divided by 2L. Okay, well, I'm getting close. I haven't gotten exactly what the book wants me to find yet, but I can see that I am heading on that path. Okay, so now I remember that I just calculated N to be PL cubed over KT, so that's my N. V bar X over 2L. And now I can rewrite that as V, the average velocity in the x direction, divided by 2 times P over KT times L squared. And while we have done part A, Okay, so part A is done. Now we're going to do part B. So starting part B, show that the equation can be written in a different form. So we want to show that we can take the equation we just found and we can rewrite it to be PL squared over square root of 4MKT. So that's what we're doing. And so now we go and we say, well, you know, in section 18.1, we have equation 18.4, and we know that Vx bar average is about the square root of V bar, the RMS speed. Okay, and so from that we can get that Vx average squared is going to be 1/3 V average squared, and we get this from equation 18.4. Well, I've already said it, from those two guys. So between those two guys, we come up with that formula. And we know that VRMS is the same as V bar squared, so that's what that, well, VRMS squared is V bar squared, so we got that. All right, so now we're going to throw those things into our original equation. We're going to have F, the frequency, V x bar over 2 P over KT L squared is approximately the same as the square root of V bar x squared over 2 P L squared over KT. Okay, so we have that. Which then can be turned into the square root of 1/3 V bar squared divided by 2 P over KT L squared, and we end up with the square root of 1/3 3 KT over M divided by 2 P over KTL squared, which ends up being the PL squared divided by the square root of 4MKT. And there's the 2, so that's the square root of 4. There's the square root of M sitting there. I have the square root of K on top. I have a K on the bottom, so I can have the square root on the bottom. And everything's fine with that, except my 9th grade algebra teacher would not like it because I am doing something weird there. Alright, now we continue with the C part of the problem. Assume the cube is air-filled at sea level and has a temperature of 20 degrees centigrade, and the sides of the cube is 3 meters. Determine F. Alright, so we want to do the C part of the question, and we know that the frequency is going to be PL squared over square root of 4MKT, because we just got that from that guy there, so that's not a real issue. And so pressure at sea level, 1.0 would be 1 atmosphere, times 10 to the 5th pascals, if I don't remember that, I could look in the front cover of my book to get it. And then I've got 3 meters squared for my length, and then I want the square root of 4. Now we need the mass of the molecules in the room. Okay, so from problem number 16, which we didn't work naturally, we find that air at 1 atmosphere is 29 atomic mass units. Okay, so we get that from that chat from problem 16, and we find, okay, well, that's fine. Then I got 29, my mass is going to be 29 times 1.66 times 10 to the minus 27 kilograms, which I got from the front cover of the book, times Boltzmann's constant, 3.8 times 10 to the minus 23rd joules per Kelvin, times, and I run out of room, 293 K, because I have, that's a time sign. And that has to go on the top there. Okay, I put the whole thing in my calculator, and I hit the enter button, and I get 3.27 times 10 to the 28 hertz is the frequency of a wall being hit. Well, that seems pretty high, doesn't it? Well, yeah, but there's a lot of atoms there, so that is probably the truth of the matter. All right, now we're looking at problem number 22. Now, why do I do these hard problems for anyway? Starting with the Maxwell equation distribution in equation 18.6. So I've got to start with equation 18.6. We're going to show that I'm going to show that the integral 0 to infinity of the function of v dv is equal to n. And for part B, we're going to go on and show that the function 0 to infinity of v squared, function of v dv over n, is equal to 3kt over n. Okay, so that's what we're doing for part A and part B. All right. So the first thing we're going to do is we're going to say, what does Maxwell equation look like anyway? And so Maxwell equation looks like 0 to infinity 4 pi n m over 2 pi kt to the 3 halves v squared e to the minus 1/2 m v squared over 2 kt dv. Okay, so the idea is to show that this guy is, if I do that, that's going to be equal to n. So isn't that just lovely? So I'm looking at that, I'm saying, well, what am I going to do about it? And so I look in the back of the book at my integral tables, and I find an integral table that in appendix B5. And in there I find something that's those integral 0 to infinity of x squared e to the minus ax e to the minus ax squared dx is equal to square root of pi over 16a cubed. A cubed? Is that what it says? Let's see. B5. Alright, so there's B5. So B5 is on page A7. So B5 is a bunch of intervals. Yep, that's what it is. And then I say, well, this looks sort of like that. I've got here. It looks like I've got something that's x cubed, and here I have something e to the minus x squared with something in front of it. So now, if I could manipulate this somehow to look more like what I have on the bottom, then that would be, then I could get the answer. Okay, and this is a cubed right there. I'll go and put it back there. Now this falls in the category of knowing the right answer, I can now solve the problem. All right, so the trick we're going to use is called change of variable. Change of variable. All right, so that's what we're going to do. And so we're going to let x equal the square root of mv squared over 2kt. And we're going to let x squared be equal to mv squared over 2kt. And we're going to let v squared be equal to 2kt over mx squared. And we're going to let v be the square root of 2kt over mx. And we're going to let dv equal the square root of 2kt over m dx. Now this is where we run into trouble because we can't see enough of our paper to know what we're doing. So hopefully you started at the top of your paper before you do that. Now if I do that change of variable, I end up with integral 0 to infinity of 4 pi n m over 2 pi kt raised to the 3 halves v squared e to the minus 1/2 m over kt v squared. Well, that turns out to be my original guy. So that's my original guy. Now I'm going to do a change of variable on him. And I'm going to end up with integral 0 to infinity 4 pi n m over 2 pi kt to the 3 halves 2 kt over m x squared e to the minus x squared times the square root of 2 kt over m dx. Okay, so I went and took the original equation, I did my change of variable, and now I have something that's even worse looking. Isn't that lovely? Well, I noticed that most of those things are constants. So if we bring out the constants, we have a 4 pi n. We've got a m over 2 pi kt to the 3/2. We've got a 2kt over m. And we have a square root of 2kt over m. And that leaves us with integral 0 to infinity of x squared e to the minus x squared dx, which is an integral that was given to us by Euler, by the way, in case anybody's thinking about that. All right, well, now I go and I do some algebra 1 on the things in front here. And here's an m, there's a m to the 1/2, and here's an m to the 1.5 on top. So the m's go away. I got a kt here, I got a kt there, I got a 2kt there, I got a 2kt, and I have a half a kt. So the 2kt's go away. And so I've got a square root of pi, and I got a pi divided by the square root of pi cubed on there. So when I get done, I'm going to have 4 pi n 1 over pi to the 3/2 square root of pi over 4, and the square root of pi over 4 is that integral. That's where that came from, square root of pi over 4. I come all the way back up to the top, and I say right there, square root of pi over 4, because a is a 1. All right, so I come on back down, and I say, oh, wow, that's equal to n. The 4's go away. I have a square root of pi on top. I have a square root of pi on the bottom. They go away. I have a pi on the bottom. I got a pi on the top. They go away. And my answer's n. So we did the A part of the question. So now we have to do the B part of the question. And probably it would be best to get a new piece of paper. So we're gonna show, now that that went so well, show that the integral 0 to infinity of v squared, the function of v, dv divided by n is equal to 3ktm. So that's what we're showing this time. And we go back to the appendix on A7, and we see the integral 0 to infinity of x to the 4th e to the minus x squared is going to be 3 over 8 square root of pi. Okay, so now we're going to go and manipulate the function that we're trying to find so that we get into a form that we can solve it, so that we come up with the answer that we are looking for. That's the whole point of the problem. All right, so the integral 0 to infinity v squared function v dv divided by n is going to equal 0 to infinity 4 pi n m over 2 pi kt raised to the 3/2 v to the 4th e to the minus 1/2 m v squared over kt dv. All right, so we did that. We're going to do a change of variable again, and so we're going to let x be the square root of m v squared over 2kt, and we're going to have x squared the m v squared over 2kt, and we're going to let v squared be 2kt over m x squared, and we're going to let v be the square root of 2kt over mx, and we're going to let dv be the square root of 2kt over m dx. And then we're going to substitute all those things in, and we're going to end up with integral 0 to infinity of 4 pi n m over 2 pi kt to the 3 halves 4 k squared t squared over m squared x to the 4th e to the minus x squared square root of 2kt over m dx. Okay, we're still stuck with a whole lot of constants, so we'll bring the constants out, and 4 pi n m 2 pi kt to the 3 halves 4 k squared t squared divided by m squared square root of 2 kt over m integral 0 to infinity x to the 4th e to the minus x squared dx, which is exactly what we're looking for. Alright, so we go in and do something. What are we going to do? It looks like we're going to skip a whole lot of steps and say that this is going to be n over 3kt over m. So we started with okay. So what that's telling us is that the integral of 0 to infinity of v squared f of v dv is going to be the n 3kt over m, which is exactly what we got from there. Okay, that's fine. And now we come up with our final conclusion that the integral 0 to infinity of v squared f of v dv divided by n, I put that n on the other side, is 3kt over m, which is exactly what we were trying to show. And yeah, that borders on a lot of things, I suppose. Alright, now we're going to be working on a problem considerably easier than that. Why should we work on problems that are easier, I wonder? Okay, we're going to do problem 26. You have a sample of water and are able to control the temperature and pressure arbitrarily. Using figure 18.5, describe the phase changes you see if you start at a temperature of 85 degrees centigrade, 180 atmospheres, and decrease pressure and temperature to 0.004 atmospheres, while keeping temperature fixed. Okay. And so what we have to do is we have to look at the figure 18.5. Okay, 18.5 on page 483, looking at figure 18.5. Initially, the water is a liquid. As the pressure is lowered, so as pressure is going down, the liquid becomes a vapor. Somewhere between 1 atmosphere and 0.066 atmospheres. The graph's not that accurate. We can't really tell exactly where it does. And it should still be a vapor. If I could spell vapor. At 0.004 atmospheres. Okay, so that's the A answer. Now we're going to look at the B answer. We're going to repeat it again, and this time we're going to have the temperature fixed at 0 degrees centigrade. Assume that you hold the system starting at the initial conditions long enough for the system to stabilize before making any further changes. Okay, so we're going to go from 180 atmospheres, 0 degrees centigrade, and we're going to keep it there and go down to 0.004 atmospheres. That's what we're going to do. And what is going to happen is initially we're going to have the water as a liquid, because it can't. What happens is at 0 degrees, when I go and turn it into ice, I expand, and with that amount of pressure, I can't expand. So as the pressure goes down, pressure decreases, the water becomes a solid. So the H2O turns to ice. And that'll happen around 1 atmosphere. And then, as I approach 0.006 atmospheres, that ice will turn into a vapor. And at 0.004 atmospheres, basically, in a little bit of time, all the ice will be a vapor. Okay, so that's all there is for question 26. We're going to do question number 30 next. What is the dew point if the humidity is 75% on a day when the temperature is 25%? So we're looking for the dew point. Okay. So we're going to look at table 18-2, and we see that when the temperature is 25 degrees centigrade, that 23.8 torr is vapor saturation. So that'd be 100% saturation. Okay. 75% humidity means 75% of that 23.8 torr. And that's going to be, using my calculator, 17.85 torr. Okay. Now we go back to table 18.2, and we see that 17.85 torr is somewhere between the 25-degree mark and the 20-degree mark. So the answer to the question has to be somewhere between 25 degrees centigrade and 20 degrees centigrade. Now it's just a matter of proportionalizing it out until we get to where we want to be. Okay. So if I take the values I know, 25 degrees centigrade minus 20 degrees centigrade, and I do a proportion of that with 23.8 torr minus 17.5. We end up with taking way too many significant digits, 37 degrees centigrade per torr. And then we say, okay, well, that being the case, if I go 20 degrees plus some increase, and we're at 17.85 minus the 17.5 that we know, times, and that's times the 0.7937 degrees per torr that we calculated earlier. We end up the dew point being at 20.28 degrees centigrade. And then we ask ourselves, how many significant digits do we have? Well, we don't have that many. So we round that off to 20 degrees is my final answer. And let that be the case. Number 34 is next. If the humidity in a room with a volume of 440 meters cubed at 25 degrees centigrade is 65%. What mass of water can still evaporate it from an open pan? Okay, so I can only make it to 100% humidity from that open pan. So the issue is, how am I going to get how much mass is in that 35% difference? Okay, well, we know that PV is equal to nRT. And so M, the number of moles, is going to be PV divided by RT, picking the right gas constant. And I think we know everything in there, don't we? So we know the pressure, 1 atmosphere. Do we know that? 34. Yeah, well, it doesn't say it's 1 atmosphere, but we'll use that anyway. So, we need to find we need to know the pressure of the water. Okay, so it's not 1 atmosphere, it's the pressure of the water. It's 3.17 times 10 to the third pascals, which I calculated separately, times the volume of the room, meters cubed, divided by 8.314 joules per mole, Kelvin times the number of Kelvin that I have. So 273 plus 25 would be 298 K is going to be the number of moles that, and this is the number of the partial pressure of the water. So that would be at 100% if I had 100% saturation in the room. Okay, so I do all that, I put it in my calculator, 563 moles of water. Now, the mass that can be added would be 35% of that, because I already have 65% of that in the room already. So 35% of the 563 moles, and then if I multiply, why don't I just multiply it out? I'll put it all in my calculator at the same time. 18 times 10 to the minus third kilograms per 1 mole. And water's H2O, so that's 2 hydrogens and an oxygen, so that's 16, and 2 from that guy makes 18. So that's where that comes from. And when I get done, I get 3.5 kilograms of water can still be evaporated into the room. Okay, I'm going to do number 38 next. 38. Air that is at a dew point of 5%. So I'm at the dew point at 5 degrees centigrade. Is drawn into a building where it is heated to 20 degrees centigrade. What will be the relative humidity at that temperature? Assume constant pressure of 1 atmosphere. So pressure is going to be 1 atmosphere. And account for the expansion of the air. Take into account the expansion of the air. All right, well, the outside air is at saturation, is what being at the dew point means. So I'm at saturation at 5 degrees centigrade. I use table 18.2 again, and I find that I'm going to have, that being the case, I'm going to have a partial pressure of water of 872 pascals, not a whole hex amount. We're going to consider that the number of moles is going to be fixed. So I'm not going to change the number of moles as I'm bringing it from the outside to the inside, and the pressure is going to be maintained the same as well. Okay, then we're going to go and look back in table 18.2 again. So I'm going to go back to table 18.2. And I'm going to look at what is saturation at 20 degrees centigrade. So 20 degrees centigrade, I'm going to be at 2330 pascals. And then I say, well, what's going to be the new relative humidity if I bring that water from the other room into this room? And so I say, well, relative humidity. And there's going to be, well, whatever I was bringing in, 872 pascals of pressure of water, and I have 330 that the room could have, but the only place I'm getting the water from is from the outside air, and I would have the relative humidity being at 37.4% after I throw that in my calculator, and that would be my final answer. You notice that the question says take into the account the expansion of the air, and notice that we didn't do that. Why not? Well, the amount of moisture I have coming in has nothing to do with the amount of air expanding or not expanding. So I just care about the water is all that I'm caring about, and so that's all that I'm going to be doing. Okay, that ends the problems I'm working in chapter 18.